Hi guys, welcome to our structural analysis lecture today. My name is Engineer Dr. Edidiomi Ambrose. I'll be taking you on the continuation part of direct stiffness method. So this is part 3 of this topic. If you haven't watched part 1, I will advise you to go back and get part 1 and then watch part 2 of this lecture, and kindly subscribe to this channel so that you will be watching our videos as we drop. This channel we give lectures on structural analysis and civil engineering on several topics. So in the first part of this lecture, we look at the introduction to direct stiffness method. We look at the basic principles of direct stiffness method. We look at the main steps in the method and then the application of the direct stiffness method in truss analysis. And in the second part of the lesson, we did solve exercises so you could get it and watch. So in this third part, we are going to look at how we can use Microsoft Excel to aid our calculations in direct stiffness method. So stay tuned and watch. Okay, so in this part 3 of the lesson, we're looking at Microsoft Excel aided analysis of plane trusses using the direct stiffness method. So as the size of the truss increases, we find out that it becomes difficult for us to solve this manually. For instance, you get a matrix that is 10 by 10 or 12 by 12 is a bit difficult to do it manually. So in such case, Microsoft can provide a simple and efficient computational tools to perform these matrix computations with ease. And so in this section, rather than use a commercial structural analysis software like the Star Pro, which you don't know what it does, we just want to use Microsoft Excel. As a young engineer, you will still have a clear understanding of the method and the processes that is carried out. So this is like a bridge between the manual computations and the use of commercial structural analysis software. So let's look at the matrix inverse approach. How do we do it? So recall that F is equal to KU, which we have derived this in the first part of the lesson. So this is the first way. What is X? X is the global stiffness matrix, U is the global displacement vector, and F is a global force vector. So if the stiffness matrix is square and non-singular, then mathematically you can make U subject of the formula, and by making U, this may becomes that inverse of K multiplied by the force vector can give you the displacement vector. So this equation K, this K minus 1 raised to power minus 1 is the inverse of the global stiffness matrix. This equation can be used to calculate the unknown global displacement based on this equation. However, in structural analysis, we don't, if you write the full force displacement equation and put it in the matrix, it will not give you a correct answer because then the inverse of that matrix will not exist. So what do we do? The right approach is to obtain the reduced force displacement equation. How do we do that? By applying boundary conditions and removing the components of all the known support restraint. Once we do that, the remaining part of the equation, we can calculate this, find the stiffness matrix, find the inverse and multiply and find our joint displacement. So this is the correct procedure. Determine the global stiffness matrix of all the members, then assemble the full stiffness matrix of the truss. After that, form the full load vector. Then apply boundary conditions by removing the rows and columns corresponding to the restraint degree of freedom. We do that, we now take the reduced stiffness matrix to MS Excel to calculate its inverse and then multiply the inverse with the force vector based on that equation 18. So let's demonstrate that by using this example too. This is a truss that is made up of 7 members and 5 nodes. The truss is well dimensioned. It has a load of 215 and 215 kilonewton. The truss is symmetrical both in load and in dimensions. Let's say all the members have a cross-sectional area of 2795 millimeters squared and rules of elasticity of 200 gigapascal. So let's follow the procedure. to analyze this trust and see. So let's look at the solution to this. So we start by breaking the trust into members joined together at the node. So we have numbered this to member 1, member 2, member 3, member 4, member 5, member 6, and member 7. We also have labeled the node. This is node 1, this is node 2, this is node 3, this is node 4, and this is node 5. And this is the applied force of 215 at node 2 and 215 at node 4. This is the, because remember that the truss we are analyzing is a pin joint here at the left support and the roller joint at this node support. So that is why when you come here at node 1, which is the left support, we have the vertical reaction, we call it RV1. And we didn't want to include the horizontal reaction because there is no horizontal force. So obviously, horizontal reaction will be 0. And then at node 5, this is the reaction at support 5. With that roller, we'll have a vertical reaction. So we call that RV5. So the dimensions are still the same. So we can start the analysis. Remember the cross-sectional area was 2795 millimeters square, which if we change to meter square, it gives us 2.79 times 5 raised to power minus 3. In the same way, modulus of elasticity was 200 gigapascal, which can be represented as 200 times 10 raised to power 9 Newton per millimeter square. So AE is now, you multiply the cross-sectional area by the modulus of elasticity, that gives us 5.59 times 10 raised to power 8. So that means for horizontal members are this one. They are 5 meters, 2.5 plus 2.5. This one, so 2.5. So there are three horizontal members, member 2, member 4, member 6. So the length of those members are 5 meter. So for those such member, sine theta is equal to 0 because already there is a horizontal. So sine theta in this case will be 0. So sine theta will be sine 0, which equals to 0. And then cos theta will be equal to 1. And so in such rules one, if you calculate A over L for each of them, it will be 5.59 times 10 raised to power 8, which is the AE, divided by the 5, which is the L. So that means for such, the AE over L is 1.118 times 10 raised to power 8 Newton. So we go for diagonal members. The L will be using Pythagoras theorem to calculate the L. In that case, remember for diagonal members, the height is 5 and the horizontal is 2.5. So we use Pythagoras theorem to find this length and it gives us 5.59. And so for those one, they are cos theta. Look at when you look at horizontal member like this one, like this horizontal members, it is inclined here to the, sorry, like this diagonal member slant, it is inclined to the horizontal by theta. So if you take sine cos theta, there will be opposite, will be adjacent over hypotenuse, which is this adjacent over hypotenuse. So that's why I have 2.5 over 5.59. That gives us 0.447. And in the same way, sine theta will now be opposite over hypotenuse. So for this theta, this is the opposite 5, hypotenuse is here 5.59. So that gives us 0.894. And so if you proceed to calculate AE over L for this member, AE had given us 5.59 times 10 raised to power 8. If you divide this by L, which is 5.59, it gives you 1.0 times 10 raised to power 8. Next thing is to go to joint displacement and degree of freedom. Now, because this member, this truss, as we have analyzed, it has how many joints? 5 joints. That is at node 1, node 2, node 3, node 3, node 4, node 5. And each of them will have 2 degrees of freedom. That is displacement in the vertical direction and displacement in the horizontal direction. So that means 2 times 5. That's why the degree of freedom of this truss is 10. For each of them at node 1, you will have at node 1 you will have U1 V1, At node 2, you have U2 V2. At node 3, U3 V3 4, U4 V4 5, U5 V5. For each of them, U stand for the horizontal displacement and V stand for the vertical displacement. So we come to the member properties. This is the properties of all the members that we have calculated. Please take note of this end node for member 1. Member 1 start from node 1 to node 2. Member 2, node 1 to 3. It is very important that you note that if you go back here, you can see here member 1 start from node 1 to node 2. Member 2 start from node 1 to node 3. It's very important that you note with the in node. So in this table, the in node for each of the 7 members is stated. This is the length of the members that we have calculated. You can see for node member 1, which is a diagonal, is 5.59. Member 2, which is a horizontal member, is 5.0. And for each of them, we have calculated the AE over L. We have calculated the cos theta for each of them and the sin theta for each of them, and the square of cos theta and the square of sin theta. And this one is cos theta sin theta. So having obtained all these member properties, you proceed to find the member global stiffness matrix. And for remember this equation which we have derived in our lesson 1, which is the global stiffness matrix is the A over L of all the C squared CS minus C squared minus CS. So this all what we do for member 1. Note that for member 1, the end nodes are 1 to 2, 1 and 2. That means that is why we have U1 V1 and then U2 V2. U1 V1 represent displacement at node 1, the horizontal and the vertical. And U2 V2 represent displacement at node 2, the horizontal and the vertical. So having known that, we now use this and pick values from this table to fill this matrix. So like this is C squared. What was C squared for member 1? For member 1, C squared was 0.200. So that is how we fill this table. So this is the global stiffness matrix for member 1. And in this global stiffness matrix, look at, we have taken time to show you the rows and the column belonging to each of the displacement. So you have this in the row section. In the column section, you have U1, V1, U2, V2. In the row section, you have U1, V1, U2, V2. So every member of this matrix can be defined in their position. For instance, if you pick this member 0.8, this is one V1 in the vertical and V1 in the horizontal. So all of them have their positions well defined. We go ahead and do the same for member 2. For member 2, the notes end notes are 1 to 3. So we now go to the table, pick value and fill. Remember that for this member 2, EA over L was 1.118 times 10 raised over 8. Remember also that in this member 1, everything is in terms of A over L, which is 10 raised over 8. So take note of that. So in order to maintain 10 raised over 8, so that the stiffness matrix of member 1 and member 2 and all the numbers will be expressed in terms of 10 raised over 8. So we need to multiply in this 1.18. So when we take 1.18, this is how we have this stiffness recipe for member 2 become like this. And in the same way for member 3, for the member 3, you have for member 3, you have in nodes are 2 and 3. We pick up value from the table, and this is for member 3. And the same way for member 4, the same thing we do for member 5, and the same thing we do for member 6. In each of these, you will notice that the matrix is defined. This U3, for example, member 5, it was node. In node was 3 and 5. So that is why you have displacement U3 V3 and U4 V4. And we use this to define. So every number here can be defined by its position. For instance, if you pick 0.4, 0.4 in the vertical is U4 and in the horizontal is V4. So we do the same. And do the same and have the stiffness method for member K7. The next thing is to assemble this stiffness matrix to obtain the global stiffness matrix for the whole truss. So what we do, since the degree of freedom for this truss is 10, that means the global stiffness matrix for this truss system will be a 10 by 10 matrix. So, and what we are going to do is to combine the stiffness matrix of this 7 member to form that 10 by 10 matrix. So this is how we do. First of all, let's pick member 1. This is a 10 by 10 matrix. And so what we do is just to pick member 1 stiffness value from stiffness matrix and place them in this one. And look at the way it is placed. Like I said, every member in the stiffness matrix is defined by vertical and horizontal. So if we go to this member 1 that we have defined, let's pick this member. This member in the vertical is U1, in the horizontal it is U1. So let's go back and the value is 0.2. So let's go back. If we go back to the global stiffness matrix for the truss, you can see here we place this is U1 in the vertical and U1 in the horizontal. So that is how we place that 0.2. And that is how we pick every other member from the stiffness matrix of member 1 and place them in this assembled stiffness matrix. So by then, every component of that stiffness matrix of member 1 is here. So we proceed by now adding that of member 2. For member 2 here, like this is a stiffness matrix for member 2. So if we pick this one, that is U1, U1. We come here, where is U1, 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 U1. So this is the place. Remember, there was already 0.2 from stiffness matrix of member 1. So we now add that of stiffness matrix for member 2. The same thing for this position. For position that there was nothing from member stiffness matrix of member 1, when you go, we only place that of member 2. And so by so doing, all the members of stiffness matrix of member 2 are now placed in this assembled stiffness matrix. So in the same way, we go and do for member 3. When we pick this a stiffness matrix for member 3, for example, when we pick this first number component, it is U2, U2. So where is U2, U2 here? This is U2 in the vertical, U2 in the horizontal is here. So that is how we add this 0.2. Remember, there was already 0.2 there, which was mostly likely either from the stiffness matrix of for member 1 or member 2. So we positioned all the component of stiffness matrix in member 3 in this. And we do the same for member 4, member 5, member 6. By the time we put all those members, at the end of the day, for each position we add, for instance, this place is 0 plus 1.118 plus 0.2, we add it to represent one number. Where it needs to subtract, we subtract it. Like this place is 0 minus 0.8, we subtract it. After we have placed the stiffness matrix from all the members. So after doing that, what we will now have is the global stiffness matrix of the entire truss system. So this is how it looks like after we have positioned and added everything. Remember that all the stiffness matrix form was in terms of 10 raised to power 8. So that is why this global stiffness matrix is also in 10 raised to power 8. So having done this, the next thing is for us to obtain our load force displacement equation. The force displacement equation is just, this is our stiffness matrix. We keep our stiffness matrix. This is the displacement vector. The displacement vector is just arrived by just the displacement at each of the node. At node 1, U1, V1. At node 2, U2, V2. Just like that to U5, V5. And then this is the force vector. The force vector is obtained by placing the load for each of the positions. For instance, here at node 1, there are two force vectors. One corresponding to U1 is should have been F1, which is the horizontal force. There is no horizontal force. That is why this place is zero. The one at node vertical, there was a vertical force here at node 1. That vertical force is actually the reaction at node 1, reaction at that support, that pin support, which we had assigned this RV1. For node 2, there is no horizontal force. That's why this place is zero. But at node 2, remember there is a vertical downward force at node 2. That force of 205 kilonewton. Why we add minus is because it is coming down. If it was pointing up, it would be positive because it's coming down. And our sign convention is that downward forces are zero, are negative. So that is why we add this minus. Why is this not 215? But 215000, we have changed it from kilonewton to newton. At node A, there was no force. No force. The horizontal component of force is zero. The vertical component is zero. At node 4, the horizontal component of force is zero. There is also a vertical downward force of 215 kilonewton. So when we change it to newton, it becomes 215,000. At node 5, there is no horizontal force. There is a vertical force that we have assigned the reaction, vertical reaction there, which is RV5. So this is how we have derived full force displacement equation for this truss that we are analyzing. In our next lecture, which is part 4, we are going to confine the reduced force displacement equation and then go ahead to analyze our joint displacement and then our member forces. So this way we stop for this, and I would advise you to subscribe to this channel so that you'll be getting our videos as we post. Thank you for watching this. Bye.